It's a pleasure to introduce Eric Urbain, who's going to give our colloquium talk tonight. So he's a mathematician of French origin who finished his PhD in '94 at Orsay University in Paris, and his advisor was Jacques Tillouin. He's currently a full professor at Columbia University, New York, and his work was acknowledged by a number of prizes and for example, he received the Lampez Distinguished Columbia Faculty Award in 2005. He was an International Congress of Mathematicians speaker in 2006 at Madrid, and he was a Guggenheim Fellow in 2007. So Eric works on arithmetic properties of automorphic forms, and one of his major achievements was the proof, half of the proof of the main conjecture for ordinary elliptic curves over the rationals. They are ordinary at a prime p, and this main conjecture has something to do with p. So this proof was done in collaboration with Chris Kimmer. The other half of the proof is due to Kazuya Kato. Okay, so I will let Eric discuss about Bernoulli numbers, Eisenstein series, and cyclotomic units.
Okay, thank you very much for the invitation and for the introduction. So here is the title, Bernoulli number, Eisenstein series, and cyclotomic units. So I will be mainly speaking about Bernoulli number and Eisenstein series, and then make a link with cyclotomic units at the end. So let's start by some motivation. So here P is going to be an odd prime number, and you probably all know the Fermat theorem that tells you that if you have a solution in integers of the equation xp plus yp equals zp, then the solution has to be trivial. One of the integers has to be 0. So if you take the cyclotomic unit, the cyclotomic field, sorry, so that means that you you add the p power root of unity to q, so that gives you a number field, and then you can think of the ring of integers inside this number field, which is zeta of zeta p. That means it just takes the polynomials with coefficient in z in this root of unity. Then if you have a solution of this equation, then you have a factorization like this. And using this factorization, if you knew that this ring here is a unique factorization domain, which means that it behaves like the integers, that means that you have irreducible elements like prime numbers, and each element in this ring can be decomposed uniquely as a product of irreducibles times some invertible element. I mean, if this was known, which means that this ring is a UFD, then in that case, using this factorization, you have to find a proof of this theorem. Unfortunately, this ring is almost never a unique factorization domain. And therefore, that proof that was found a long time ago was actually false. But Kummer could somehow save that proof under a certain condition, is that the class number of this ring, something I'm going to define later, as an order which is prime to p. So such a prime is called a regular prime. And so Kummer proved that if P is a regular prime, then Fermat's last theorem is true for this prime number P. So, of course, then one question is that what are the regular primes? And this is the beginning of a story. So let me first remind you what are the Bernoulli numbers. So you consider the Taylor expansion of this function in T, and you just look at the coefficients Bn of Tn over n factorial, so that means that the nth derivative of this function at 0. This is easily seen to be a rational number, and so those numbers are called the Bernoulli number. So if you can compute the first few ones, so you have B1 equals 1/2, B2 equals 1/6, then you can check easily that Bn is going to be, B2n plus 1 is going to be 0, so the odd Bernoulli numbers for n bigger than 1 are zeros, and then you have B4 equals 1 minus 1 over 30, and so on. So Kummer proved in 1850 that if P does not divide the product of B2 times B4 times BP minus 3, then P is a regular prime. And I mean, from this description of the Bernoulli number, it's not difficult to compute a few of them, and then you can compute enough to check that some primes are regular primes. And for instance, the first irregular prime is 37, and then you have 59, but you have many of the primes are actually regular. So that gives you a proof of Fermat's last theorem for many primes. It's still unknown if there are infinitely many irregular primes. But on the other hand, it's a theorem that there are infinitely many irregular ones. So you can generalize this definition of Bernoulli number in the following way. So you take chi a Dirichlet character modulo n. So what is that? So you just consider the group Z mod nz. So this is, and you take the inversible element, and the Dirichlet character is just a group homomorphism from chi from this group to C cross. Okay. So if you take such a character, then if you take an integer a, you compute chi of a is going to be 0 if a is not prime to n, and otherwise this is just the value given by this character. So it's why you can. It makes sense to. It makes sense to do this computation from a equals 1 to n minus 1, and so you look at this power series now, which has coefficients in C, and then you can define the generalized Bernoulli number like this. And so if you do that for chi, the trivial character, and n equals 1, you can check that you recover the same number. So an important example is when n equals 1, and you take chi, a Dirichlet character modulo this capital N, and then in that case, B1 chi is given by this function. Okay. So it's easy to compute also. Okay, so the first refinement of Kummer criterion is given by a theorem of Herbrand-Ribet. So for that, one needs to introduce some notations. So G is going to be the Galois group of Q of theta p over Q. So what is that? This is just the set of homomorphism of Q of theta p that preserves Q. Okay. So that means automorphisms that preserve addition and multiplication. And so we can consider a group homomorphism from G into Z mod P Z cross, which is defined by when you apply this automorphism when you apply the automorphism sigma to the p power root of unity, then you get another p power root of unity to some power, and this power is called omega of sigma, and it is defined modulo p. And actually, because theta p is a primitive root of unity, sigma of theta p has to be also a primitive root of unity, and it's why this omega of sigma has to be non-zero modulo p. So this group, this map actually defines an isomorphism between the Galois group and Z mod PZ cross. So G acts on the class group of Q of theta p. So the class group is something that measures the defect of the ring Z of theta p to be a principal domain. So a principal domain is a domain where every ideal is a principal. So you just look at the set of non-trivial fractional ideals. And so fractional ideals is just a finitely generated module inside Q of theta p, which is, and we assume it is non-trivial. And when you have two of them, you can multiply them. Just multiply elements inside them. You get a new ideal. So that gives you a group structure. So if you divide by the subgroup of principal ideals, then you get a group that is closed a class group. And when this class group is trivial, that means that every fractional ideal is principal. Okay, so it really measures this defect. And so it can be shown that this group is finite. It's a sum of Minkowski. And so now you have a natural action of this Galois group G on this group here. And because this group G is abelian, you can decompose every module over which it acts like this. Oh, yeah, sorry, I forgot to say that C here is just a p-silo subgroup of Q of this class group. So this is the maximal subgroup of order power of P. And then you can decompose this group C as a sum of C of I, where C of I is the maximal subgroup of C for which G, this Galois group, acts by this character omega to the power I. Okay. So you have such a decomposition because those characters omega to the I actually, when I runs from 0 to p minus 1, gives you exactly the set of all characters of G. Okay. Maybe I should say that so omega goes from Z mod PZ, sorry, goes from G to Z mod PZ cross, but this is a set of p minus 1 root of unity, and this you can embed this in C, okay, in C cross. So the character omega, you can see it as a character taking values in C cross, and therefore you can also see it as a Dirichlet character modulo p. And actually it has even the following property that if you take omega of A, then this omega of A is going to be an algebraic integer in C, and you can check that omega of A is congruent to A modulo P in a certain sense. Okay. So this character omega is called the Teichmüller character. It's very important in this theory. So, so you have this decomposition. And the theorem of Herbrand-Ribet shows the following. If you take I, an odd integer between 3 and p minus 2, then p divides h of I. H of I is the cardinality of C of I, if and only if p divides the Bernoulli number b p minus I. Okay. So if you compare this to Kummer's criterion, you see that b2, b4, bp minus 3 are exactly the cardinality of, are going to be related to the cardinality of h p minus 1, h p minus 2, and so on. So, so it's why this theorem can be seen as a refinement. So it can be seen as a so here you of course you can see that the even integers here are not considered. So you may wonder if this is really a refinement of a Kummer's criterion, but it is one because Kummer proved that if p divides h of I for some even integer I, then p has to divide h of I for some odd integer I. So it's why this is really a refinement, and moreover, it's more precise because it's going to tell you that p is a regular prime if and only if p divides this product. Here. Because Kummer criterion was just a sufficient condition. Here you have a necessary and sufficient condition. Okay. So there is a further refinement of the theorem of Herbrand-Ribet, which is the theorem of Mazur-Wiles. So before, it's important to remark that using the very definition of Bernoulli numbers, you can show that you have this congruence modulo p. So if you look at bp minus I, then this is going to be 1 omega minus I. And therefore, if p divides p minus I, then if and only if p divides this generalized Bernoulli number. And so Mazur-Wiles proved actually something much more precise. It showed that if I is between 3 and p minus 2, then h of I, which is the cardinality of CR of I, this is the power of p, has the same periodic valuation of this Bernoulli number here. So that means that the power of p, the maximal power of p of b1 omega minus I is the same as h of I. So therefore, this b1 omega minus I gives you the exact size of h of I. So before explaining a little bit about this, the proof of Mazur-Wiles theorem, let me give a link between Bernoulli numbers and L functions. So if you take a Dirichlet character, chi, then you can consider the L series Ls chi as a sum from 1 to infinity of chi of n divided by n to the s. And you can check easily that this is convergent if the real part of s is strictly bigger than 1. And actually, you can show that it has a meromorphic continuation to the whole complex plane, and that there is a pole there is only a pole at s equal 1 and when chi is a trivial character. In that case, this series is just a Riemann zeta function. Okay. And actually, you can show that using this, the formula that gives you the meromorphic continuation or the holomorphic continuation when chi is non-trivial, that you can evaluate s at 1 minus n, where n is an integer greater or equal to 1. And you can see that the value at 1 minus n is actually a rational number. Algebraic number when chi is non-trivial. But if chi is trivial, this is a rational number. And you have the following formula. The value at 1 minus n of this L function is given by this generalized Bernoulli number. Okay, and so you have these conditions here. So here is the idea of the proof of Mazur-Wiles theorem. So this idea is based on Ribet's ID, but it uses Iwasawa theory and finer study of some congruence condition. So first, there is one part which is to relate the class group to a Galois group of some maximal abelian extension of Q of theta p, here. T of I is, so you look at L, the maximal abelian extension of Q of theta p. So abelian extension means that this Galois group has to be abelian. And L is maximal for that. And this L has to be unramified everywhere. So what does unramified mean? So if you have an extension of field, L over K, and if you have P a prime number, sorry, a prime ideal in OK, OK is a ring of integers of K. So saying this is unramified means that if you look at OL modulo POL, this guy has no nilpotent. Okay. And this is exactly the same notion as if you have a covering of curves. Covering of curves, the notion of being unramified for a covering of curves is exactly the same as being unramified for the map from spec OL to spec OK, for those who knows what a scheme is. So anyway, so here is this, the class fit theory tells you this. So therefore, studying C of I is equivalent to study this Galois group here. And it's equivalent to find abelian extension of Q of theta p, which are unramified everywhere. So this is the first step. The second step is to prove that, so using congruences between Eisenstein series and cusp forms, and their associated Galois representations, to prove the divisibility that this L value, the value of this Dirichlet L function at 0, divides the size of H of I. So that means that it divides the size of this group here. And this is done by using congruences between Eisenstein series and cusp form. I'm going to explain what they are next. And the last ingredient is that we have a formula like this. Is that the product of those L values for odd integers, which is the same as H minus, is the same as H minus, which is the product of H of I for odd i's, from I equals 3 to P minus 2. So if you have all those divisibilities for all I between 3 and P minus 2, plus this equality here, you deduce actually the equality of those of B1 omega minus I in H of I up to a periodic unit. Okay. So let me explain what modular forms on Eisenstein series are. So a modular form of weight k and Eben-type chi being again a Dirichlet character, is an holomorphic function on the Poincaré upper half plane, H, satisfying this relation here. So the Poincaré upper half plane is a set of complex numbers of imaginary part positive. And so you can see easily that if you take a matrix A, B, C, D in SL2 of R, then this matrix acts on the Poincaré upper half plane by this transformation, the Möbius transformation. And so this AZ plus B divided by CZ plus D is still belong in H, and you have you must have this relation. So gamma naught of n here is a set of matrices A, B, C, D with A, B, C, D in SL2Z now, so, and such that n divides C. Okay. And that forces A and D to be prime to P. So it's why you can, it makes sense to write chi of D here. So a modular form is a function like that that satisfies this transformation. And there is another condition which f of z has a limit at each cusp of gamma naught of n mod h. So gamma naught of, h modulo gamma naught of n gives you a Riemann surface with, which is an hyperbolic surface which has cusps. It's not compact, but you can compactify and make it a Riemann surface. And so you have to compactify, you have to add a few finitely many points, and each of those points are called cusps. And so one of them is a cusp at infinity, is when the imaginary part of these goes to infinity. So you need to have that, for instance, f of ix goes to infinity when x goes to infinity. Sorry, f of ix has a limit when x goes to infinity. So there are operators acting on this space of modular forms called the eq operators. So for each prime q, you can define a tq of f given by this formula here. And you can check that this tqf is again a modular form. And so we say that f is an eigenform if for each prime q, actually tq of f is just a multiple of f. And so you have an eigenvalue, which we call aq of f here. And if you look at, you see when you look at this transformation for the matrix 1, 1, 0, 1, you see that f of z plus 1 equals f of z. So therefore, f has a Fourier expansion. And because of the fact that it has limit at cusp, this Fourier expansion actually is just restricted to a non-negative integer. So you have an expansion like this. And so if f is normalized so that a1 is equal to 1, then in that case, you can check that all the other coefficients are algebraic integers. And moreover, that aq of f here is the eigenvalue of tq. Okay. This is not very difficult to see from this formula. So this is what modular forms are. So Eisenstein series are a special case of modular forms. So if you take an integer k greater or equal to 3, you can form this series here, and you can check that it is convergent. And from its definition, you see that this function has to satisfy this transformation, has to be invariant by this transformation I defined before. And that's probably the easiest way to construct a modular form. And actually, you can do that also when k equals 2, but when k equals 2, this series is not convergent. So you have to add a complex variable and show that you have an analytic continuation, and then evaluate at s equals 0. So if you renormalize this function, what you get is something like this. So you get the Fourier expansion of this Eisenstein series after renormalization is given by this. So the constant term is given exactly by this L value, L1 minus k chi, divided by 2. And then the Fourier coefficients for integers bigger than 1 are just given by this very simple function. It's just the sum over the divisor of n, which are prime to capital N, and you just do chi of dt k minus 1. So this is a very simple function. So this is very simple. On the other hand, this number is quite mysterious. And as I explained before, it is related to Bernoulli numbers. Okay, so it's basically given by a Bernoulli number here. And you can check also that this modular form is actually an eigenform. And the eigenvalue is given by this 1 plus k of k, qk minus 1. Okay. So now, or maybe before. So you see, I explained that when you look at the Fourier expansion of a modular form, which is normalized, an eigenform which is normalized, then these coefficients a0, a1 here are algebraic integers. So therefore, it makes sense to say that if they are divisible by prime numbers or prime ideals of a number field. So when f is cuspidal, it means that the constant term here is 0. And actually, this is for the cusp at infinity, but for all cusps, this constant term has to be 0. So this is what it means for f to be cuspidal. If you look at an Eisenstein series, the constant term is given by this value, which is a Bernoulli number, which is non-zero. And therefore, you see that Eisenstein series are not cusp forms. But on the other hand, if p divides this number, then modulo p, this Fourier expansion looks like a cusp form. And so this is the main idea of Ribet, is that if p divides this L value, or if p divides the Bernoulli number, then the Eisenstein series looks like a cusp form, so therefore there is a congruence between an Eisenstein series and a cusp form. And the point is that the property of Galois representation attached to Eisenstein series and to cusp form are very different. And using this, he was able to prove his theorem. So let me explain now why. So it's why I'm going to have to introduce Galois representation now. So if f is an eigenform of weight k in a bond type of chi, then it's known thanks to the work of Eichler, Shimura, and Dölling that one can attach a Galois representation taking values in GL to ZP. So what is ZP? So first, so GQ is just the Galois group of Q bar over Q. Okay, so this is a profinite group. So the group of automorphism of Q bar. Okay. And now ZP is a ring of periodic integer. So you can think of an element x in ZP as a power series a naught plus, so yeah, okay, so a naught plus a1p plus a2p squared 3p cubed and so on. So if you take a real number, you know that you have you can consider a decimal description of your real numbers, and so you can think of a0, a1, a2, a3 as the decimals here, okay, but just for the prime p. And so of course, if you look at this in the real numbers, this is not convergent, but in ZP, you have a topology such that for this topology, p power n goes to 0 when n goes to infinity. So it's why this series makes sense. And so a rigorous way to look at this is to define ZP as the set of sequences x, let's say x1, x2, x3, and so on, where xi belongs to z modulo p to the power I, z, and such that, so when you project this to z modulo p to the I minus 1 z, then xi is sent to xi minus 1. And basically, the xi is when you look at this until ai minus 1, pi minus 1. Okay, so when you look at this element here, this is exactly the pi approximation of your periodic integer. So periodic integers are very useful to study congruences in a very consistent way. So you can think of ZP as something that patches congruences. So you have a Galois representation from GQ into ZL to ZP, and satisfying the following condition. If you take the trace of Frobenius Q by this group morphism, you get AQ of F. So Frobenius Q is an element of the Galois group such that Frobenius Q of theta is theta to the Q, okay, for some p power root of unity. I mean, you have many elements that satisfy this, but there is the fact that it's saying that it is unhomified means exactly that it's independent of this choice of the choice of this element. Okay, and such that the determinant is given by the cyclotomic character to the power 1 minus k times chi. Okay, so the cyclotomic character is the character that gives you the action of the Galois group on the p power root of unity. So I'm not going to be more precise about this. And so one of the properties of this Galois optation is that if p does not divide AP, then the restriction to the inertia at p has the following shape. Okay. So the inertia are just the subgroup. Okay, I'm not going to describe the inertia subgroup here. It's past half an hour, so anyway. So, so what is important about Cus forms is that the corresponding Galois optation is irreducible, absolutely irreducible. And on the other hand, if F is an Eisenstein series EK chi, then the corresponding Galois optation is reducible, and actually it has exactly this form. If you remember the eigenvalue of the Eisenstein series here, you see that this is exactly the trace of Frobenius Q for this Galois optation. When you apply Frobenius Q to this, you get exactly chi of Q times Q chi minus 1 plus 1. Okay, so therefore what happens is that, so I said before, so if p to the m divides L1 minus chi k, that means that E k chi looks cuspidal modulo p to the m, and therefore that means actually that there exists G a cusp form of same weight and level as E k chi, such that G is congruent to E k chi modulo p to the m. And so in general, G is not necessarily an eigenform, but if G is an eigenform, you deduce that the corresponding Galois optation, rho G, becomes reducible modulo p to the m. And on the other hand, G being cuspidal, rho G has to be irreducible. So you have some representation which is irreducible that becomes reducible modulo some power of p. And so using this, you can show that you can find a stable lattice, stable by Galois, so that the representation rho G on this lattice, modulo p to the m, has the following shape. And with the following shape, such that this star here is non-trivial. So saying that this star is non-trivial means exactly that you have constructed an extension of Galois optation of the trivial character by this character here, chi epsilon 1 minus k. And extensions are classified by group cohomology. And here this is therefore a class that gives you a class in the group cohomology with coefficient z mod p mz with action given by this character. So you can show that it's unmamified away from the level, away from n. And you can show also this is unmamified at p. And the reason is because of the reason is because of the shape of the restriction to the inertia here. You see that the extension here is reversed compared to this here. So it's why this star has to be 0 when you restrict to inertia. So using this, you can show that actually p to the m divides this, and actually p to the m divides you can show that p to the m divides the size of this group here. And therefore, that means exactly what we wanted is that that this Bernoulli number divides h of I. Okay, and so that was this was proved first by Wiles, assuming that the class group C of I is actually cyclic, but it required more work to prove that it was true in general, and this is the work of Mazur-Wiles. It's much more complicated than that. Of course, you have to use also Iwasawa theory and periodical functions for this, but it's just technical details. The main ideas are here. So now I want to speak about cyclotomic units. So if you take a number field f, q bar, and an integer n, you can consider the Kummer map from f cross to h1 f zp of 1. So let me explain this. So if you look at the exact sequence mu pn of q bar cross. So mu pn is just the p to the n power root of unity inside q bar. And then you have q bar cross here, and the map here is just x gives x to the power p to the n. Okay, so this gives you an exact sequence of Galois module. And if you look at the long exact sequence attached to this short exact sequence for the cohomology of the group GQ, what you get is, so you do that for Galois of q bar over f. So when you do that for Galois of q bar over s, what you get is mu pn of f, then f cross, so this is x gives xp to the n. And then you go to h1f, this group here, which is called f, mu pn. And so mu pn is actually isomorphic to z mod pn, z, but with an action given by a character, which is this character. This is a cyclotomic character. It's why we put 1 here just to remember that the Galois action is not trivial, but given by a character. And so if you look at this map here, but you just take the projective limit over n, what you get is exactly this map here, okay, which is called the Kummer map. Okay. So that means that from this map, you see that whenever you have an element in f cross, you can define an extension here, an element of this Galois cohomology. And so if you, moreover, if you take a unit in f cross, what you get here is an extension which is actually unramified. Okay. So the cyclotomic units are special units in Z of theta n. So units means invertible elements of this ring. And there are units which are generated by elements of this form. Okay, so theta n is a nth primitive root of unity. And if you look at this product here with a any integer and rb such that the sum of the rb is equal to 0, then you can show that this is actually a unit. And in fact, if n is divisible by at least 2 prime number, you can even show that 1 minus theta n is a unit. So cyclotomic units are important because if you look at their image by this Kummer map, you get an element Cn here that goes in H1 of Q theta n Zp of 1. And it satisfies the following norm relation. If you take the co-restriction from Q of theta NL to Q of theta N of this CNL, then you have either 1 minus Frobenius L inverse applied to Cn or Cn. Another way to see it is that if you take the norm of 1 minus theta NL from Q of theta NL to Q of theta N, you get either 1 minus theta N or 1 minus theta N to the power 1 minus Frobenius L. So a system of cohomology classes satisfying such relation is what we call an Euler system. And so Euler system have been discovered by Kolyvagin in the 80s, or maybe a bit earlier. And it was used to prove some cases of BSD conjecture. So the point is that there is another proof of Mazur-Wiles theorem that was explained by Karl Rubin using ideas of Taine, Francesco Taine, and Kolyvagin. And so the proof works as follows. I mean, the main ideas are as follows. So you have to use those class Cn to construct torsion classes. So theta n is theta n belongs to this cohomology group here, when F is Q of theta n. So it has no torsion here. This is just a torsion-free module, no p-torsion. But it is over Q of theta n. But if you use those classes, you can actually descend to Q, but to the price of having a class which is torsion, which is called kappa n. This class kappa n is obtained by what we call the Kolyvagin derivatives. So you have to apply some elements of the Galois group of Q of theta n over Q to this to the class Cn, and then use the norm relation to show that actually modulo p to the n for some integer n, then you get a class that descends to Q. And moreover, it satisfies precise ramification conditions. So there is this the question of those classes. Now, by the way, now those classes are what are called the Kolyvagin system by the work of Mazur and Rubin. But the point is that using Tate and Poitou-Tate duality theorems and the reciprocity law of class field theory, then you can show, I mean, this is the work of Rubin, that actually h of I divides this value. And this is for I, integer I from 3 to p minus 2. So now if you have such divisibility, and you use again the class number formula, then you can deduce again the Mazur-Wiles theorem. So of course you can notice that this divisibility is the exact opposite of the divisibility proved by Mazur-Wiles. So in other words, if you use this technique and Mazur-Wiles technique, you can prove the theorem without using the class number formula, which is here. And this is quite important because the class number formula is really something that is known only for number fields. In general, it's something that is not, I mean, impossible to obtain directly, like the one for number fields. So it's important to see that if you use Eisenstein congruences and Euler system, you can find exactly the proof of Mazur-Wiles theorem. And this is important because in other situations, because this Dirichlet class number formula is not available, then you cannot use only one of the two divisibilities. You really need to prove two divisibilities. So if you combine the Eisenstein congruences on Euler system, then you can therefore, as I said, prove the Mazur-Wiles theorem without using the Dirichlet class number formula. So another example of this is the case of an elliptic curve having over Q, having a good ordinary reduction at P, and such that the as-surveyed function at 1 does not vanish. And so you have to assume that it has no p-torsion point over some abelian extension of Q, and there are some other simple technical conditions. But from this, you can show that the p part of the BSD formula holds, which means that if you take the L value, this L value divided by the Nérontate period of the elliptic curve, then up to a periodic integer, then this is the size of the p part of the Tate-Shafarevich group, times some Tamagawa number for the primes dividing the conductor of the elliptic curves. So those numbers are just some numbers that give information about the ramification at those primes. And the conductor here of the elliptic curve is an integer that, I mean, this is a discriminant of the elliptic curve. Okay. The elliptic curve is given by an equation y squared equals x cubed plus px plus q, and the discriminant of this degree 3 polynomial is given by this number here, ne. So this theorem is obtained by first proving one divisibility, that this number here divides this number, and this is done using an Euler system by Kato. Kato constructed an Euler system. Instead of using cyclotomic units, he used Siegel units, which are units on the modular curves. And then with Chris Skinner, we study Eisenstein congruences, but not for GL2, but for the group, the unitary group GU22. And to find that if these L functions, I mean that this L value divides the size of this group times this Tamagawa number. So, I mean, it's not as simple as that, because again, we have to use Iwasawa theory to make this work precisely. But this is the main idea. So what I've talked about before are ordinary Eisenstein congruences. So now if you can consider non-ordinary Eisenstein series in the following way. If you look at the Eisenstein series E to chi and you just make this transformation, then when you do that, you can see that the constant term of this modular form now is 0 because of this transformation. And therefore, this critical, I mean, we call it critical Eisenstein series here, looks cuspidal. I mean, in the theory of periodic modular form, it's actually a cuspidal modular form. Cuspidal periodic modular form. And basically, it means that for any integer n, you can find a cusp form, Gn of weight Kn, so that Gn is congruent to this Eisenstein series here, modulo p to the n, and where Kn converges to 2 periodically. Okay, so you have these congruences, and n is not fixed. You can find such congruences for any n. And once you have these congruences, moreover, you can actually assume that Gn is an eigenform here. So when you have this congruence using the same idea as before, you can construct an extension as before, and you can do that for each n, and you can patch those congruences, and basically what you get is going to be an extension, C chi, that lives here. So Qp here is just Zp where we have inverted p. So this is a field. So we have an extension here in here, which is something, which is a subgroup of H1Q of theta n, where the action of Q of theta, of Galois of Q of theta n over Q acts by chi. But with this problem is that so C chi's here are defined up to an element in QP cross. If we want that those classes define an Euler system as before, we need to make sure that those classes are integrals. and that they satisfy some norm relation. So this leads to the following questions. So the first question is the following. Can we normalize the class as C chi in a canonical way so that if you consider Cn defined by 1 of the size of Z mod n Z cross times the sum of the C chi when chi runs inside the Dirichlet character modulo n, then you get something which is integral. Okay, and if this question can be answered positively, then we can ask, can we relate so Cn to Bernoulli number, or can we, or to L values, or equivalently, are the Cn related to the cyclotomic units, 1 minus theta n using the Kummer map? And in other words, I mean, you have the following question that, can you prove Mazur-Wiles theorem using only Eisenstein congruences? So that means without invoking the class number formula nor cyclotomic units. So I'm going to finish by this theorem, saying that actually there is a positive answer to the 3 questions above. And so if you use the Mazur-Wiles theory, you can express this in this way. So if you take an odd integer a between 1 and p minus 1, for each integer n, there is a class Cna in the Iwasawa cohomology of Q of theta n, where the action of Z mod Zp Z mod Pz cross is given by the character omega a, and constructed using Eisenstein congruences only, and satisfying the norm relation of an Euler system. And moreover, if you take this class for n equals 1, then C1a is actually related to the omega a branch of the Kubotel-Leopold periodical function. And therefore, once you have this, you can, of course, using the techniques that I've explained before, you can prove the Mazur, you can refine another proof of the Mazur-Wiles theorem. Not another proof, but you can, you get the proof of Mazur-Wiles theorem using only Eisenstein congruences. So let me give you 2 remarks. So the non-triviality of the classes constructed here come from the non-triviality of the classes C chi constructed above. And the norm relations follow from the very definition of the construction as well. Because you have a normalization factor that comes from the ordinary Eisenstein congruence number, which itself is related to L values. So constructing the CNA is not too not yet. The CNA is constructed are non-trivial, they are satisfy the norm relation. This is not too difficult. The hard part is to prove that they are actually integral. And so I have 2 proofs for this. So one that is kind of reassuring because it shows that those classes are actually the correct one, and it uses Stiglberger theorem. Stiglberger theorem is a weak form of the conjecture of Mazur-Wiles. So of course, if you want to prove the Mazur-Wiles theorem using the Mazur-Wiles theorem, is not very good. Although here Stiglberger theorem is much weaker. But so what was interesting is actually to find a proof which is completely different. And so there are another proof that is using actually the local global compatibility of the correspondence in the periodic Langlands program for GL2QP, and using Pascuna's formalism of blocks for those representation. And so the interest of this second proof is that actually it allows generalization to construct new Euler system. And so I hope to get new Euler system in the future using this method. So I think I'm finished. Thank you.